Okay, welcome back. We've got the next question. This is no longer a short answer question. This is where we get more involved into doing the actual circuit analysis on the page. This question is asking us use superposition to find the voltage across R5 right here, which is a 6K ohm resistor. For each source, draw the circuit you're analyzing before doing any circuit reduction. In your analysis, you can perform circuit reduction and use any circuit analysis method for each circuit source. Indicate the voltage contribution at the bottom of the next page. Blah, 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 blah. Okay, so let's do the first thing. So superposition means we're going to consider, we've got to identify the active sources, which in this circuit would be this voltage source, this current source, and this current source. Everything else is a passive component. And what we're going to do is we're going to turn off two of the sources and just keep one source in. Redraw the circuit. That's what they mean by for each source, draw the circuit you're analyzing. We'll analyze it and then move on from there. Turn off that source and then turn on the other sources successively, one at a time, doing an analysis every time. Okay, so first, some reminders. We're going to assume this is the ideal world. In the ideal world, there is no resistance through a current source. There's absolutely no resistance through a current source. In the ideal world, of course, there's... scratch that. Let me back that up. In the ideal world, there's infinite resistance through these current sources. So if these are turned off, no current could flow through them, nor this one. But if in the ideal world, if this is turned off, there's absolutely no resistance through the voltage source. So when we turn this off, this is a closed circuit. When we turn the current sources off, they become open circuits. So on our first step, we're going to keep the voltage source turned on. We're going to turn off the two current sources and redraw our circuit. So here we go. I'm just going to put the actual numbers because it'll go faster. Again, this is a test, so speed is important. We're keeping V1 turned on. But now the current source here is going to be turned off, so this turns into an open circuit. Again, we're actually trying to find this voltage. I'm just going to call it V5. We're looking for the voltage drop across that resistor. Again, here, this is going to become an open circuit. If this is an open circuit and there's no current flowing through it, essentially we can ignore this part of the circuit. That really won't be there. So I don't have to draw this part because it won't factor into my analysis. So there's the circuit. So I've drawn the circuit. Now we're going to do some circuit analysis and try to figure out the voltage drop just due to this active voltage source across this resistor right here, V5. Okay, so now that I've drawn that, I'm going to redraw it in a way that makes sense to me as I do my analysis. And you don't have to do it this way, but you got to do what makes sense for you. So I'm right here at that node. At that node, this is going to split into a 2K and a 6K along that branch. And it also splits into this branch, which is just an 8K resistor. And then they come together right here. So that's that part of the circuit. Then at this node, which is this node right here, we get a 2K resistor which flows right in series with a 4K, which flows right in series with a 6K, which is actually our resistor of interest. And then we come back along here and complete the circuit. So we've simplified this circuit greatly now. We can see immediately that these two will combine in series to be an 8K, and then these two will combine in parallel to become a 1 over 8K plus 1 over 8K, which is just equal to some equivalent resistor, or if you recall, that should just be 8 times 8 over 8 plus 8, or 64 over 16. Notice how the numbers work out very nicely. This is a test. They want speed, and I would suggest you show them the greater your logic flow like this, very quickly but briefly. And so 64 divided by 16 is 4. So we can replace this with just a equivalent resistor of 4K right there. Then the 4K will add in series with the 2K and the other 4K. So basically there's a 4K, 2K, 4K. I'm just going to indicate that they're in series. And so 4 plus 2 plus 4 is 10K. So 10K equivalent resistor. And then finally I can actually redraw the circuit one more time. And I've got a 10K and a 6K. And this is basically a voltage divider circuit. So the voltage right here, which is what I'm interested in, V5. So V5 is going to equal to V1 and then divided by the voltage divider circuit, which would be 6K over 10K plus 6K. So I've got V1 times 6 over 16, which is equal to V1 times 3 over 8. So that's this is the contribution of voltage due to V1. It's V1 times 3 over 8. And I'm going to stop there, and then we'll pick it up with the next current, with the other two active sources.